Okay, it's a couple minutes early, but I'm just going to start and make a few announcements. So, as I had already posted on Piazza, we are supposed to have a class this Friday because Friday follows a Monday schedule, but I've canceled that class because I am actually not here this Friday. Okay, so for those of you who didn't know, now you know that there is no class on Friday, but there will be a makeup class on Tuesday, which is an out of cycle class, but because I'll miss the Friday lecture, I need to make up for it. That class will be held in this room on Tuesday at from 2:30 to 3:45. Okay, I'll send another email or a Piazza post with the email notification so that those of you who can come, please do. I know some of you might have another class at that time. If that's the case, somewhat unfortunate, but this was the only time the room was available, so I couldn't find a different time for the room. Okay, so that's one thing. The other announcement is about some of the things that we've been giving out. As I had mentioned, Lab 3 came out a few days ago. Lab 3 requires you to deploy your code that you develop on Amazon's cloud. Okay, to facilitate that, we have created accounts for you on something called AWS Academy, which gives you free credits to run your code on AWS. And for you to understand how to do that, we gave out a lablet earlier today, which is the cloud lablet. Okay, that lablet really walks you through how to use AWS Academy to access Amazon's cloud. Okay, how to start machines on the cloud, and you can just use free credits to do that. The only thing I'll say is once you're done with your work, shut down all the machines. Otherwise, they keep incurring cost, and eventually you'll run out of all the free credits. Then you will not be able to use them for the lab. Okay, so just don't forget to turn things off once you're done, because they will keep incurring costs otherwise. Okay, that's the only thing I really wanted to mention. But if you have any questions about accessing AWS, tell us and we can try to help. Okay, so this is kind of the last lab where you're deploying your code on the cloud and trying to make it a cloud application, right? Okay, so that's a good segue to the topic that we are going to cover today. So we are done with the core topics that involved everything from clock synchronization to transactions to consensus. So now we are going to switch gears and come back to practical applications of all of those concepts that we've been talking about for the last maybe 7-8 classes or so. Okay, we'll start with the web today. Okay, and then we'll look at other topics like file systems and middleware in the next several classes. Okay, so today's class and maybe next class is going to focus on the World Wide Web. I'll talk today about web applications, web services, and so on. Okay, and next time we'll talk about web caching and content distribution and how that actually ties into some of what we have been talking about in terms of caching and cache consistency and replication. Okay, but let's start simple. We'll start with web applications. This is a picture that by now all of you should be familiar with. We spoke about this in the second or the third lecture. This is a typical client-server application using the web, where the client machine is the browser, the server machine is a web server. Okay, and in today's class, we are really going to dig deeper into how these server applications are built, how they can be scaled up, and so on. Okay, so that's the thing you want to keep in mind. So let's talk about the server component. Okay, so this is a pictorial view of the Apache web server. Okay, Apache is an open source Apache web server, or the HTTP server. It's an open source project. Is the most popular web server that's actually used on the internet today. Typically, if you go to a website, any website, it's highly likely it's actually running Apache. Okay, there are other web servers as well, but this is the most common one. Okay, this is what I would call the functional or component view of Apache. Okay. Early on, when we were talking about building server application, I showed you a different picture which involved a threaded application where you had requests coming in. They came to a dispatcher thread sent them to a thread pool. That was basically the threaded view of the application, because this is a multi-threaded and a multi-process server. Okay, but this is the functional view. assuming a request comes in, okay, and a request has been handed off to a thread, how does the thread process that request? Okay, so this is the path it's going to take. It's pipeline processing. Okay, so essentially the requests are coming into an Apache core. Okay, they're going to be handed off to some thread, and then the thread is going to process the request in some number of stages. Okay, and so in the Apache architecture, these stages are called hooks. Each hook is going to actually cause the request to be processed by one or more modules. Okay, modules are components that perform specific types of processing. So for example, if you have SSL, which is secure socket layer, the request contents may come in encrypted. So you might have to first decrypt that request in order to process it. Okay? And then you can have all kinds of server-side processing. For example, if you have things like JavaScript and so on, those are modules that can plug in that Apache can call for specific types of processing. So your request will go through many stages, and then it will essentially complete and exit the system. Okay? All of this is essentially a single process as far as Apache is concerned. So this is not a multi-tier type scenario, but these are all stages inside Apache. So it's a modular architecture. It's essentially, you can have different modules that plug in. You can configure Apache in different ways, depending on what you want Apache to do. And then that's how it's going to process each request. Okay? So keep this picture in mind. We'll come back to it in different contexts. Okay? But this is essentially a functional view of the Apache web server. Okay? Now let's talk about a couple of different things, and we'll come back to web applications. The other concept, in addition to the web server, that I wanted to mention is the proxy server. We briefly encountered proxy server in lecture 3, where I said you can go from a client server architecture to a client proxy and a server architecture. And the proxy is the intermediary that's sitting in between a client and some sort of a server. Okay? Proxies can perform all kinds of services. Okay? In this example, the proxy here, which is a web proxy, is performing what is called protocol translation. Okay? So our web server, or not a web server, our server here is a FTP server. It allows you to do file downloads. Okay? It only talks FTP. Okay? Now, if you want to expose these file downloads through an HTTP interface, you can put a web proxy in front of it. Okay? Requests are going to come from clients as HTTP requests to download files. The web proxy is going to translate them. Okay, this is where it's doing protocol translation from HTTP to an equivalent FTP request, get back the response, and back an HTTP response. Okay? That's just one example of a proxy. Proxies are useful in a variety of different contexts. So another example could be this server, not an FTP server. It's a media server. It's just a server that's capable of streaming videos over the internet. Okay? And this device here, or a browser here, may be running on a small phone. Okay? So let's say the video content that's on the media server was encoded for a large screen. Yeah, so maybe it's for a laptop screen or even a television. But now you want to watch that content on a small screen. Okay? So what the proxy can do is it can bring the content and do what is called transcoding, where it converts the content from one format to another. So it can make it tailored for a smaller screen. It can reduce the resolution, do all kinds of translation, and then send it to the browser. So this is an example where it's changing the content. Okay? So proxies can do protocol translation. They can do content transformation. They can do other things like caching, as we will see, lots of different use cases. Okay? So we'll get back to proxies maybe next class. Okay? Today, we are mostly going to focus on the server and think about web applications and so on. But keep this in mind, that in the web world, proxies are used extensively for all kinds of different use cases. Okay, is that clear? Okay, so let's get back to web applications. So we've seen this before. This is a standard picture of a multi-tier web application where the server actually has multiple components. The first tier here, this is our Apache server. Okay? It's only talking HTTP. Okay? Typically, you would take the application logic and put it into a different component, which is in this case shown on a different machine altogether. And then you can put the data itself on yet another component. That's your data tier. So typically, you have a web tier, you have an application tier, which is called CGI here, but that's a really old way of writing web applications. These days, you write them in Python or any modern language, or things like Node.js, JavaScript, and so on. So you write your application here that sits in the middle tier. The backend tier is a database. Okay? That's our three-tier architecture. Okay? And we are going to now build on that and try to do a variety of things with that basic architecture. Okay? All right. So with that recap, let's now talk about web cluster. So let's say you want to take an application, a web application, and scale it up to lots of users. Okay? So how are we going to do this? We are going to make a cluster of servers. So this is where we'll replicate that web application onto multiple machines. Okay? So you will have a front-end machine where requests will come in. The front-end machine will send the request to one of those replicas. The replicas will process it, send back the response to the front end, and the response will go back to the user. Okay, is that clear? Okay, so now what if each of those web servers are multi-tier applications, web applications? What are we going to replicate? What are we not going to replicate? So think about what I showed you here, right? So rather than a simple web server, your application actually has three tiers, right? So here I only shown you a replica as a single box, but it could be each of them could be a three-tier application, right? So that brings up several interesting problems. First is, let's say you have a database, right? So you have put a database here. So each of these things has a database, and maybe it has a second tier sitting in front of it. Okay, this just takes whatever I showed you on the previous slide and has actually replaced each of these replicas with a three-tier application with a database at the back end. Okay? That's one way to do it. But now if you do this, you have multiple copies of that database. Okay, you will have to implement some consistency protocol to ensure that your data is consistent. If one of these replicas makes a change to the database, let's say it's a shopping website, the database has some product catalogs and it has order information and so on. So if you make a change in one, you have to then replicate it to all of the others. Okay? So in database world, trying to do this replication can be expensive because consistency is something that database people care about a lot, because we talked about asset properties and so on. And if you remember, I said these are all expensive to implement at some level, especially when you're replication. So another approach is, let's just get rid of this. So another approach is you can still have your multi-tier application, but you don't replicate the data tier. So what you can do is you can put an application tier. I don't know why this is not. You can put this application tier, and then there's a single database tier that they all talk to. Okay, so there's a single database tier at the top, and then the HTTP server is replicated, the code is replicated, but the data is not replicated. So there's only single big database that's serving as your backend tier. So in this case, you've gotten rid of the need to maintain consistency across database replicas. Your code is still replicated, so you're still getting some scalability, because now you can process multiple requests in parallel across replicas, but the database, there is no replication of the database. Okay? This has simplified the way you have to deal with consistency of data. Okay? But with one caveat, which is if your application is query intensive or it's IO intensive, the database tier will become a bottleneck because you have only one of those. Okay? You have replicated the other tiers, but to reduce the problems of trying to maintain consistency, you said you will only have one database. Okay? So that's a pretty common approach that's used for writing your web application, where you don't deal with a lot of the database issues. You just keep one big database, you put it on a big machine, okay? And then, but everything else is replicated. Okay? This reduces the need to maintain consistency, okay? Which is something that you will see in lab 3, because you are going to replicate some of your tiers in your application and try to maintain consistency. Okay? This gets around this, but you can still have a backend as your bottleneck. Okay, is that clear? So this is one way to build a web cluster. But now let's dig in a little bit more into how the application itself, the end application or the browser, interacts with all these components. So here is an example where you have the client component shown on the left, and there are all these other components that are shown that are essentially part of the server. This is not even a multi-tiered component. This is just showing a single front end, which is the switch here with multiple web servers. But you will see that there's a lot of things that have to happen to make this seamless from an applications perspective. Okay? In particular, this is going to show you a slightly different way of processing requests than what I showed you on the previous slide, and we'll go back and compare them. So in this case, what will happen is this is your browser. The client is going to send a request to the front end, which is called the switch here. Okay? So the switch or the front end will have a URL and an IP address. That's what is advertised to the external world. So your browser is going to connect to the switch. Okay? The switch is going to then have to send it to one of the replicas. There are two shown here. The switch actually sends it here, okay, to the one at the bottom. As you will see, the request comes here. This web server actually talks to a dispatcher and say, there's a new request, which replica should process it. In this case, the dispatcher actually says, send it to the other server. Okay? So you will see now that request has been forwarded to that web server. That web server will then process that request, and you will see the response is directly going from this web server back to the client. Okay? In this example. Okay? If you look at the previous example, okay, you will see that requests are coming to the front end. The front end is sending them to one of the replicas. The replica send the response to the front end, and then the front end sends the response. Okay? So there's one scenario where all the requests and responses are coming from the front end. There's another scenario which is shown on this slide where the response directly goes back from the web server to the client. Okay, so the question is, why would we do this as opposed to the simpler approach where all the interactions of the browser are actually going through a single point, which is the front end node of the application? Is the question clear, or what we are talking about? Yes. Okay. So one point that's being made is if the session is persistent, you can go through the switch. If it's non-persistent or stateless, you can go directly back from the server to the client. Okay, that is indeed true. But here's another thing that you can think about. Right. So let's say this. Think about this client. It's a web browser. Okay, web browser sent an HTTP request to this node, this IP address. Okay, and then the response came from some other machine that you didn't even contact. Okay, so now should the web browser take this response because you sent a request to some website, some other server sent you a response? Why would you even want to take that response? Because you don't know where this response came from. Right? So if you implement something like this, there are some subtleties you have to deal with. First question is, why bother? Why shouldn't this web server send a response to the switch and switch should send it back? That's the first question you should ask. This is what is shown here. Everything is flowing through this node, the front end node. Okay? The reason you don't want to do this necessarily is the front end node can become a bottleneck because all the traffic is flowing. Incoming traffic is going through here, and the outgoing traffic is also going through that node. So that node could potentially be a bottleneck. Okay? Because it's all of this. If this is a very large website, think about lots of these replicas, this node can easily become a bottleneck. So the less work it has to do, the less are the chances it will become a bottleneck. So if you at least take the responses out of the front node and send them back directly, maybe there's less work for the switch to do. Okay? That's one reason why in this case, the response went directly from the web server to the client. Okay? So that's now, having said that, we should still say, but here is a different machine that is sending that request back to the client. Is that a good thing from a browser's perspective? Okay? The first thing is that the browser will not actually accept a response that came from a machine that it did not contact, right? Because that's not how browsers are designed. You make a request, you're expecting to get a response back on that same from that same machine. Okay? So this, if you don't do some extra work, will not even work from a browser's perspective. So what this web server will do is when it sends back a response, it will actually at the TCP packet, it will replace its IP address with the IP address of the switch. Okay? So that when the response is received at the client will think the response came from the switch. Okay? Because if you think about how does the browser know where the response came from, all the packets are coming with the source address, which is the address of the sender. Okay? So when a packet comes, you will see what the sender is, and then you know where it came from. If the sender is the same machine that you contacted, you will not actually know at a browser that the response came from the web server, which is different than the switch, because the switch is so the web server is masquerading the IP address of the switch for this to work. Otherwise, the browser will reject the response. It will not even accept it. Okay? Yes, question. Yeah, the question is, can you set up a persistent connection that will avoid all of this? That's your question. So we can indeed do that. In fact, I want to mention 3 different ways by which you can implement what I've been talking about. One is called HTTP redirect. The second is called TCP slicing. The third is called TCP handoff. These are 3 different approaches that allow you to essentially have the switch send the request off to some other node, and the response will come directly from there. Okay, so the first thing you could do is HTTP request comes to the switch. Okay, the switch can ask the dispatcher who is the server to serve it. If that's the server, you do what is called an HTTP redirect, which means you forward that HTTP request to another node, and then that node sends back an HTTP response. Okay? When you do an HTTP redirect, the client is told that the request has actually been redirected to a different node. That's the simplest way you can achieve this, which is, and the HTTP has its official way of forwarding request to another node. It's called a redirect. So you just forward that request. Okay? So then the client will then expect the response to come back from some other node. Okay? That's one way to do it. Second way to do it is called TCP handoff. This redirection this is also a form of redirection, but it's a way to do it at the TCP layer, not at the HTTP layer, which is what was happening here. You will see that it says handoff TCP connection. Okay? When you do a TCP redirect, okay, the machine that has received it, when it sends back a response, needs to actually pretend like it's the original machine that did the redirect. Otherwise, the REST client will get confused. It set up a socket connection to machine A. Responses to anything you send on the socket is coming from machine B. That does not work. So you want, when you do TCP redirects, okay, you are essentially going to have to do what is called masquerading of IP addresses, so that the response is, it looks like they're coming from the right machine. Okay? That's the second approach. Okay? And let me now talk about a third approach. This is called TCP splicing. Okay? What TCP splicing means is essentially you have an intermediary, which is the switch for us. The client sets up a TCP connection with the switch. The switch sets up a TCP connection with a backend server. Okay? And these 2 connections are spliced. Everything that's coming on the TCP connection, okay, is then simply copied onto the second connection. So you're just copying things back and forth. So that 2 TCP connection is like you're pasting them together, so it looks like data is directly flowing from the sender to the server that was actually serving the request. So in this case, for example, you will have a TCP connection from here to the switch. The switch would have to then set up another TCP connection to that web server. Everything that comes to the switch is then basically simply copied on that TCP connection, not processed, simply copied, which is like you're forwarding data. It goes to the web server, and the responses are copied back. Okay? So this is essentially 2 TCP connections that are just relaying things back and forth. So it looks like you have a direct connection from the client to the server. Okay? So these are all ways by which you can essentially implement these front-end switches or load balancing that allow you to essentially have lots of servers, okay, behind the switch. And you will now see that in some cases, the servers are hidden. Remember this replication transparency that I talked about? Maybe there was even a midterm question on it, right? So if you do things like what is shown here, okay, where you only talk to the front end, and the front end sends all the data, gets the response come. This is replication transparent. The browser does not know there are multiple machines, only sees the front end. Okay? But if you do any of these other techniques, which is redirect, splicing, or handoff, the response is actually coming back from another machine. In some case, the presence of that machine is hidden because the replica pretends to be the switch, pretends to have the IP address of the switch and does not reveal it. In cases like HTTP redirect, it becomes visible. Okay? So these things have different trade-offs and different overheads to how you go about implementing this cluster of servers. Okay? Lots of these are networking details, which I don't really expect all of you to understand at a full detail, but you should at least understand the basics of what I'm talking about. Okay? Any questions on this? So there are a few other things I want to mention because there's a question about persistent connections, which is what I did want to get to. So the switch itself can essentially schedule the request either at a request level or at a session level. Okay? So if you schedule your data at a request level, what happens is every time a new request comes in, a new HTTP request comes in, the switch can then potentially pick another replica to serve it. Okay? Because if you do least loaded, a request comes in, you pick the least loaded server, that request is sent off to that server, and then you get a response back. This works well if you have stateless applications because any replica can serve any request. Okay? But if your application is stateful, you can no longer do this because let's say you are in an e-commerce application, you put something into a shopping cart. Okay? The shopping cart of your application is state. Okay? That is basically for your session, okay, that state of your session. That's what you want to potentially buy, so you put something in a shopping cart. Okay? That the shopping cart is actually maintained at one of the servers. Okay? Specifically, it will be maintained at one of the replicas that handle the request where you said, put this in my shopping cart. The next request goes to some other replica. That replica will not have that state of the shopping cart, okay? Because it's stored in memory on some other machine. So in this case, you want to essentially do session level scheduling where all requests of a session, okay, maybe the session itself is persistent, but regardless of whether it's persistent or not, all requests of that session are always sent to the same replica. Okay? So that any state that you kept is now consistent. You will not actually miss it. Okay? The only other way to do it is that you have to put the state on disk. Okay? And if the request goes to another server, you have to first load that state back from the disk. So the session state is now reconstructed on a new server, and then you serve the request. But that's going to add overhead because now you are essentially keeping state on disk. So that's going to add I/O latency to your request. Okay? If you want to keep the state in memory, you have to use session level load balancing and session level scheduling. For stateless applications, and request level is good enough. Okay? So lots of details that you have to think about when you build your web application. Is it stateless? Is it stateful? Okay? And if it's stateful, then how are you going to do the load balancing? Are you going to keep the state in memory? Will you keep it on disk and so on? Is that clear? Any questions here? Okay. All right. So the next thing I want to mention when we talk about these clusters is this notion of elastic scaling. This is something that you will see large applications implement. They're not typically implemented in small applications, but let me motivate what elastic scaling even means. Okay? So let's say you have a web application. Let's say it's a shopping application. Okay? And you'd say you replicated it on 4 machines. Okay? You assume that there'll be some load coming in, and you put it on, you have 4 machines serving all your load. For normal days, maybe 4 machines are fine. Okay? Then maybe you decide that you are going to have a sale for your store. Maybe it's a Black Friday sale. Maybe you're going to have a Memorial Day sale. You have some sale. Okay? And you expect that because you are giving good deals to your customers, more customers are going to visit your website on that day, okay, to shop. Okay? Now, if there's a lot of interest in the kinds of products you're offering or the prices you're offering, a lot of customers are going to visit that site, and maybe 4 machines are not enough. All 4 machines get overloaded, and then the site does not respond to users. Okay? So the site is effectively overloaded because the volume of requests that's coming in, okay, cannot be served by the static number of replicas you have deployed. Okay? And then your site stops functioning. Okay? This often happens. You probably have encountered some website that's overloaded and not responding to it. Okay? Essentially, the number of requests that are coming in has overwhelmed the number of servers that are present. Okay? So then you can ask, what can you do in this case? The site is overloaded, what do we do? You can increase the number of servers, right? So if we say there are 4 servers, okay, that's the replication factor is 4. 4 servers can't handle the load. Okay, let's add more servers. Okay, so you can add more servers, and then maybe those larger number of servers will serve your load. Okay, but then the question is, who is going to add these servers, and when is that going to happen? Okay, maybe the site administrator is smart enough to realize, okay, there is a sale coming up. Our normal 4 servers is not enough. So before the sale start, they put maybe 4 more servers. So they double the capacity. Okay? And then when the sale hits, all is good. Okay? So maybe you are good that way. Okay? So if this change of capacity can be done by a human administrator, where they take proactive measures to decide what the capacity is. Okay? But maybe they don't know how popular the sale may be. They say, let's double the capacity. But maybe the sale is so popular, you actually needed 3 times the capacity. So then your site may still be overloaded. Okay? So it's not often possible to predict what the load will be for events that are popular, or maybe it's a news website. Okay? This often happens on a news website. Big news story breaks. Okay? Many news sites just crash. Okay? The bigger the news story, the worse the traffic, and they will just crash. Sometimes news website gets 10x, 50x traffic. That's 50 times more than normal. Okay? That's a very large number. Okay? So they can't anticipate. News stories, when they break, you cannot anticipate typically, right? So they can be unexpected things that happen. So you cannot do what you could potentially do if it's a shopping website, and you could provision this capacity. Okay? So that brings us back to this notion of elastic scaling, which says, why should the administrator do this? Why can't we build that functionality into the system? Okay? The system can monitor the load on the servers. When the load is rising and it exceeds the threshold, then add more servers, because if you don't, then the load might rise further and the servers might get saturated. Okay? So you could simply monitor the incoming load and see the utilization of servers. If the servers, let's say, every time the load on the servers goes above 80%, you said that is too close for comfort. Maybe now the server will saturate. Let's add replicas. Okay? And then if the load goes below a low threshold, maybe all the servers are sitting at 10%, you might have too many replicas. Let me reduce it. Okay? No different from dynamic thread pools. Okay? When the load went up, you added more threads to serve your incoming request. Here you're actually adding hardware capacity. You're adding servers. Okay? Saying, I need more server capacity or less server capacity. This is called elastic scaling. Okay? You dynamically vary the capacity of the web application based on the workload. Okay? So we'll add more servers. Okay? Then you'll make sure the code is deployed on the server. You will tell the switch that there's 1 more server or n more servers, so the switch can then start sending new requests. All of that has to happen, but it can be automated. Okay? All large websites are actually automated. Okay? So that's the concept of elastic scaling. They actually come in 2 flavors. One is called horizontal scaling. The other is called vertical scaling. Okay? In horizontal scaling, you vary the number of replicas. Okay? You add more servers or you reduce the number of servers. So what you are varying, okay, is the number of servers. Okay? In vertical scaling, you change the size of the server. So instead of saying I have a 2-core machine, I add a 8-core machine. So it still has more capacity. You didn't add more servers, you put a bigger server to replace a lower capacity server. Okay? That's called vertical scaling. You're changing the capacity vertically, which means you're adding more capacity or less capacity to the same number of servers. In horizontal scaling, you change the number of servers with time, okay, as the workload changes. Okay, these are 2 ways you can do elastic scaling. Okay? And then there are other ways you can also do this. One is called proactive. The other is called reactive. Proactive says you can actually look at the workload. Maybe you can predict the workload in the future. You can use some technique, which is forecasting or machine learning techniques that say, given this trend, what's the next hour going to look like? And then you provision the capacity now so that you can actually address the workload increase in the next hour. That's called proactive. Okay? Reactive says, monitor the workload now, and if the workload rises above some value, the threshold, okay, add capacity now. You're reacting to changes. You didn't do it ahead of time. You're doing things on the fly as the workload changes. Okay? So you can have both of these techniques as well. Okay? So you can do horizontal, vertical. Each of this could be proactive or reactive. Okay? All large websites that you will see will have elastic scaling built in, okay? Because they don't want a case where there's a sudden increase in traffic and the site just buckles. Okay? Because that's lost. If it's a shopping website, that's lost revenue. Okay? You're turning away customers who could have bought more products, you could have made more money. Right? So you don't want your revenue to be lost because you designed your website poorly with less capacity than it needs. Okay? So they will all implement this technique. In fact, if you actually go and look at cloud documentation, anytime you're deploying a web application, okay, cloud platforms actually give you this capability for free. Okay? You can actually turn on elastic scaling for a web application, and then the cloud platform will do this for you. So you don't even have to write extra code. You can just say, this is a web application I'm deploying, okay, add elastic scaling, and they will have a load balancer, and they will actually provision your servers for you. Okay? So you can even not have to do this yourself as a web developer. Okay? You can have the cloud platform do it for you. Any questions here? Yes.
Or do we borrow servers other customers?
Okay, question is, are the servers that you are adding to this application, are they idle servers that you are just adding, or did you borrow them from other customers? Right? So it is the former. If you are a cloud platform, let's say Amazon, Azure is Microsoft's cloud, there's Google Cloud. They are all very large data centers. You should probably know this from the data center lecture. So these are very large data centers. They are provisioned for some very high capacity. Okay? So typical utilization of a data center will be somewhere between 20 to 50%. Okay? Which means up to half the machines will be idle, because you can have customers come in. Forget this. The cloud service model is customer comes in, says, I want 10 machines, and maybe in an order of minutes, you give them 10 machines. Right? So when you have this type of environment, you better have extra capacity, because you might have lots of customers showing up asking for machines. So they are over provisioned. So there are always, there's a idle server sitting in the cloud, and this elastic scaling is simply asking for these servers on the fly and adding them to the pool. Okay? You're not going to another customer saying, I'm taking your server away. Okay? Nobody is going to like that if you say, I'm going to take your server, give it to some other customer. So that does not work, okay, for most part. Okay? Inside an enterprise, that might be okay. Okay? So if you are essentially a single enterprise, you can take capacity from lower priority applications and give them to higher priority applications. If you remember when we were talking about cluster scheduling, and I mentioned Borg, which was Google's cluster scheduler, I did mention there that when the interactive load goes up, you can take machines from batch workloads, which are, let's say, ML training, and give them to interactive. So in Google's case, if YouTube workload goes up, okay, they can borrow capacity from these batch applications and put it towards YouTube, so that your users are going to get better customers. Right? So, but that's a different case. That's a single enterprise. That's a very large one. If you are talking about traditional cloud, you will get idle capacity machines and put it for this elastic scaling. Any other questions here? Yes. Okay. Question is, vertical scaling, can we do that when the server is running? There are many ways to actually do vertical scaling. I gave the simplest case where I said you have a 2-core machine and I can put that application on a 4-core machine. Okay? Now it so happens that you actually may not have to switch servers at all, okay? Because the way the cloud allocates machines is you have a physical server and you are constructing VMs on that physical servers and simply allocating VMs. Okay? So there may be idle cores sitting on that VM that are unallocated, or sorry, on the physical machine. Okay? So rather than moving the application, what you could simply do is you can take the unused cores on that physical machine and just give it to the VM. So the VM suddenly has more cores. So it just looks like it's running on a bigger machine. Okay. So you can do these kinds of things. If you, I don't know if the lablet on the VMs asked you to change the number of cores on the fly, probably it didn't. But one of the things virtual machine technology allows you to do is you can actually add and remove cores to VMs. Okay. So you can give it more capacity while it's running. You don't have to shut it down. So you don't actually need to physically move it onto a bigger machine. You could do that too, that you can just do live migration, which we also studied, right? So you could live migrate the machine and then it just lands up on a bigger server, or you could essentially allocate more cores to the VM if there are idle capacity on that server. So many different ways to do vertical scaling. Okay, is that clear? Any other questions here? Okay, so we'll talk briefly about microservices, which I mentioned before as well. You used a simple microservice architecture in your lab, right? So you probably know now what this means. So rather than having a single server for the application tier in a multi-tier application, right? You break that tier into smaller pieces. Okay, so each of them is called a microservice. So your app tier of your multi-tier application now has many components. Okay, each component is its own small service. They all work together to build the bigger web application. That's the idea of a microservices architecture. Okay, so many web applications may have tens or hundreds, or some of them have thousands of microservices that are deployed to implement the bigger application. So it can be quite complicated. Okay? You built one with 3, I think, right, in the lab. So that's a very simple one. But most of these will actually have a lot more of these microservices that are working together. Okay? And the idea is, if you build small microservices, it gives you a modular architecture, because each microservice is designed for a very specific task. Okay? That's the task it performs. It has a well-defined interface that allows other microservices to interact with it. Okay? So each of them can be deployed independently. They can be upgraded independently. Each of them can be scaled independently. You can apply elastic scaling to now microservices. You don't have to scale the entire code of the application if one component was bottlenecked. Right? In the previous case, if you had a simple 3-tier application, your vertical scaling applies to the entire application tier. Right? But maybe only one part of the application is bottlenecked. If you had a microservices architecture, your code is now split into containers. Each of them is a different component. You can scale each one independently. Okay? If only 2 microservices are overloaded, you can just elastically scale those microservices and leave the rest. So it allows you much more fine-grained ability to do both clustering and scaling. Okay? So these are some advantages of a microservice architecture. Okay? I'm going to show you a picture that explains how you scale microservices and in some sense also web applications. Okay? So there are 3 axes here. The x-axis called horizontal duplication, but it's really scaling by cloning, which means replication. Okay? You create multiple replicas, okay? Which is the web cluster that I showed you. Okay? So this is basically scaling code. Okay? The y-axis is what is called functional decomposition. Okay? So this is, so you take the application, you split it into components and you scale it. So when you build something using a microservice architecture, this is what we did. Okay? We took a bigger application, which is what you had written in your lab 1, okay? And you split it into pieces, right? So you functionally decompose it into pieces. Now each of those can be scaled independently. So that is essentially functional decomposition. That's the y-axis. X-axis just says that you just replicate. Okay? And then the z-axis is what is called data partitioning, which says rather than having all your data in the single database, okay, one way to scale it up is not to replicate the database, but partition the database. Okay? So what does this mean? So let's say you have some number of users. Okay? You could say users 1 through 100 are assigned to this database. Okay? All of their data is here. Users 101 to 200 are assigned to this other copy of a database, which is running on a separate machine. Okay? So all of their requests go there. A third one goes somewhere else and so on. So that's essentially data partitioning. Okay? So you can partition data, you can partition code, and you can replicate code and data. Okay? So these are 3 different ways of scaling your application. Okay? Is that clear, what I just said? So one way you want to think about data partitioning is, let's say using an example that you're all familiar with, let's say web email, right? So you have Google Mail, or you may have these web mail services. You can think about a number of users that this service has to support, okay, on the order of tens or hundreds of millions. Okay? So you're not going to have one machine serve all of them. Okay? The way that's going to be provisioned is certain users are mapped to certain replicas. So when you log in, you are assigned to some group of servers. When somebody else logs in based on their name or user ID, they may be mapped to some other group of machines. Okay? And so you are essentially partitioning your user internally and mapping them to different machines so that you can scale the system. Okay? It's not like any Google server that can serve any user. Your data is kept, your mail data in this case is kept on certain number of machines. So internally it'll split you and redirect. You will not see this because you are only interacting with the front end, but in the back end, that's what is actually happening. Okay? So this is better than replication, because if you replicated all the data, you have to deal with consistency. So partitioning gets away from replication. It allows you to scale by splitting the data and putting them on different machines and then redirecting requests to different machines. Okay? That's a different way to scale than you replicate all the data, keep it consistent, and any request can go to any machine. Okay? Two different approaches. Is that clear? Yes.
How is the data partitioning?
Okay, good question. Question is, how is data partitioning going to deal with server crash? Right. So if you had only one copy of the data, you will, and if the machine crashes, you can't deal with it. It's gone. Right. So you will need to keep at least one backup copy somewhere in the system, or maybe more than one. If you're doing Paxos and so on, you'll have more than one copy, but there has to be at least another copy somewhere. But it's not full partitioning. You can essentially have a backup copy that's just sitting there, and you're just sending all the writes to that copy, and when the primary fails, the backup takes over. That's one approach. Okay? The other approach is, of course, the machine can go down, but maybe you're taking tape backups or something, and it'll take you some downtime. You'll restore it, and then you'll bring it back up. But that involves downtime and potential data loss. Okay? So when you do data partitioning, okay, as always with data, crashes are hard to deal with. Okay? Because there are only two ways. You actually replicate it, but light degree of replication, where there are two copies of everything. Okay? But you still have to keep them consistent, as opposed to n copies, which increases the cost. Okay? That's one approach. The other approach is that you will essentially keep it on tertiary storage, on some tape backup, and then bring it back online. Right? So these are ways that you will have to deal with this. That clear? Any other questions here? Okay, so let's talk about HTTP now, the protocol, and we'll look at how HTTP works and what are some nuances we got to deal with when we deal with web applications. The first thing is HTTP is a protocol where it's a request response protocol. You make an HTTP request, okay, and you will get a response. Okay? And let me show you that there are 4 or 5 types of HTTP requests that you can make. Okay? The simplest request is a GET request. You probably dealt with this when you built RESTful services and so on. A GET request basically asks for a document. Document comes back. A PUT request is the opposite of GET. You can send a document. Okay? A POST is also a way to send data, but typically a POST is used when you're filling a web form where you are sending some information that the user has filled. You're sending that to the server, as opposed to a full document that you're sending. A PUT allows you to take a file and actually upload it to a server. A POST just allows you to send some arbitrary strings of information to a server. They're both sending information from the browser to the server, but they're slightly different from one another. A delete allows you to delete a document. Okay? Typically, you will not see any HTTP server supporting delete, okay? Because you shouldn't tell the server go delete some files that belong to someone else. But where this is actually used is if you are using a browser front end to actually access, let's say, cloud storage. Okay? Maybe it's a Google Drive, right? So if it's your files, you can use HTTP delete to delete some document from it, for example. But in typical web applications, you will not see delete being supported. You will see mostly GET and POST being supported. Okay? And head is a special call that returns the header of the document, not the document itself, but just its header. Okay? So these are standard HTTP methods. Okay? The most common one is a GET request. Okay? This is what the web browser will send, get a document, and get it back. But you have to remember that there are other types of HTTP requests as well that are used in some specific cases. Okay? But assuming you send a GET request, okay, the response that is going to come back to you can be of many types. Okay? You might get an HTML file as a response. That's a text document. Okay? You may get an image as a response. If you are sending an HTTP request to get an image that's embedded in a document, you may get an image back. You could get an audio file back. If you click on a audio data that's embedded in a web page, what's streaming to you is an audio file. You can have a video file as well. Okay? You can essentially download documents like PDF, and you can click on a PDF link, you get a PDF, and you can have multi-part where it's actually concatenating different types of information and sending it back in a single request. Okay? So when a response comes back from the server, okay, it has to first indicate in the response what type of information is being sent. Okay? Is it text document, and is it a text HTML? Is it image JPEG, or is it video MPEG? And then you actually send the data. And the reason you do this is the browser needs to know how to interpret what's coming back. Okay? You just get some bytes, you don't know what it is. Right? So you have to actually include the type of information that's coming back as part of your HTTP response. Okay? So we'll send a request. Typically, when the response comes back, it will have a type associated with it, and the data or the payload is the actual information that's included that actually has that requested content. Okay? So that's our standard HTTP request response. But now let's look at the protocol itself and try to understand it a little more. Okay? So HTTP has gone through many iterations. Okay? It started with version 1. Okay? That was maybe almost 30 years ago now. Okay? Then it went to version 1.1, and it stayed there for a long time. Okay? And then recently, your version 2 of HTTP came out. There's a version 3 that's being designed. So in the past few years, there's been a rapid iteration. But for a long time, the typical HTTP versions are either 1 or 1.1. So let's try to understand those first, because they're still widely used. Then I'll talk about what HTTP 2 does and what benefits it offers over 1. Okay? So HTTP 1 is also called non-persistent HTTP, is the simplest way to do HTTP, which is every time browser wants to set up an HTTP connection to the server, it will set up a new connection. It will send a single HTTP request. You will get a response. You will shut the connection down. If the browser wants to then send additional requests to the same server, it will set up additional connection. Okay? Each is a separate connection. Each HTTP connection will have one request and one response. Okay? That's shown in this picture where there's a browser. It's setting up a connection to a web server that's a shopping site. You'll see that there are 3 connections here. Okay? So maybe it went and got some information, then it put something into a shopping cart, then it did something else. Each is a request that a connection that you set up. So you'll set up a TCP connection, then you'll send HTTP request, get a response, close the connection. Okay? That's non-persistent HTTP. Okay? Now, as you can imagine, every time you set up an HTTP connection, you have to pay the overhead of setting up a TCP connection. And you remember the 3-way TCP handshake that incurs some overheads. Okay? So HTTP designer said, this is expensive. If a browser makes multiple connections to the same server, why close the connection after the first responses come back? Let's keep it open. Okay? So that the browser can send multiple requests on the same connection. Okay? So that was the addition they made to HTTP, and that version of HTTP was called 1.1. Okay? So it's also called persistent HTTP. Okay? Some of you may have used it in your lab. So here you set up one connection to the server. Okay? You can send one request, get back a response. The connection stays open. If the browser wants to send another request, it can use the same connection is already open. Just send the HTTP request, get back a response. So you have saved the overhead of setting up a new TCP connection. Okay? And you can do this multiple times. You can send multiple requests, get multiple responses. Okay? This is persistent HTTP. Okay? Now, the problem with persistent HTTP is that all of these requests and response have to be sequential. Okay? So you have to send a request, get a response. Until the response comes, you cannot send the next request. Okay? So this can be a problem because let's say you have a web page in the web page has 6 images in it. Okay, so you will first make an HTTP request, gets the HTML web page. Then the browser will look at the web page and say there are 6 embedded images. You have to download them from the server. Let's say all the content is on the same server. Okay, now in this case, you have to fetch them one at a time, because you have to get the response before you send the next request. Okay? So you'll get the first image, then the second image, then the third image. By the time you're done with 6 images, some time has passed. The user is sitting there waiting for their page to load. Okay? Because you are not seeing the images load, and it's just taking some time. Okay? Now, if you are done non-persistent connections, you could have, after you got the first page, set up 6 connections in parallel. Okay? Ask for all the 6 images in parallel, download them in parallel, and then the content gets to you faster, assuming you have enough bandwidth. Okay, bandwidth is not the problem. You can essentially parallelize your connections and load your content in parallel. Is that clear what I said? So if you set up multiple connections, okay, whether they're persistent or not is orthogonal. If you set up multiple connections, you can load content from the server in parallel. If you have a single connection, okay, especially in HTTP 1.1, you are going to be doing sequential requests. You send a request, get a response, only then can you send a next request. So for this reason, okay, persistent HTTP is not very useful when you are actually talking to content-rich websites, because often to load the web page, the browser has to make many connections to the server. Okay? And if you use a single persistent connection, then you are sequentializing all of your content loading, and it's going to take a long time. So your browser would rather prefer to set up multiple connections, load things in parallel. Okay? So the whole purpose of then creating this persistent connection is lost, because anyway, to speed up performance, now you would rather have multiple connections. But the reason we had this is we said we didn't want too many connections. So the browsers basically do not use this feature as much. Okay? Especially when they're loading a single page, they would rather have multiple connections. Is that clear what I said? But if you are going to make connections apart in time, maybe you click on a link, you read that web page, and after you are done, you hit next, and then you can still use that connection, because that connection is sitting there idle. You can do that. But if you're loading a single page where it has n embedded items, this is not the best way to do it from a performance standpoint. Okay, so what can we do? Any thoughts on how we can improve this? Okay, so you have a persistent connection. You want to somehow make use of it. Yes.
If maybe there's some way to maintain the persistent connection that allows asynchronous.
Okay, so you can have persistent connection. You can have asynchronous responses. Yes, that's a good way to do it. You have something. Sorry, threading. Okay, so explain what you mean by threading here exactly.
On the same connection.
Okay, so you are talking more parallelization than threading, but yes. So what both of you said is actually the case. So let's say you have persistent connection. The problem with HTTP 1.1 is it is making everything sequential. Okay, you could say, why should that be? Why can't I send multiple requests to the server on the same connections, okay, and get multiple responses? Okay, the only problem if you do that is, since you have multiple outstanding requests, you could have multiple outstanding requests. When a response comes back, you need to know which request is this response for. Okay? Maybe you sent 3 requests for 3 JPEG files. Okay? 1 JPEG file has come over the network. Okay? Now you need to know which of the requests should give this content. So long as you can solve that problem, you can use a single connection and essentially have parallel, not parallel, but concurrent requests go on that connection and concurrent replies come back. Okay, so that is essentially what HTTP 2.0 did. Okay, after many years, the designers of HTTP said this persistent connection is not really getting the benefits, because browsers prefer to set up multiple connections to speed things up. Why not use pipeline? Pipelining means we get rid of sequential connections, you can just send as many requests as you want. Okay, the browser server will send responses. Okay, the responses can also be interleaved, meaning you can get one part of image 1, another part of image 2, another part of image 1, and so on. So they don't even, the responses don't even have to come sequentially. You can actually take the response, chop it up into smaller packets, and interleave the packets. They all get reconstructed at the other end. Right? So this is going to give you the benefit of essentially trying to use parallelism. Okay? That's number one. Right? So the second thing HTTP 2.0 does is it actually takes the headers, which are all text-based, and makes them binary. Okay? Which means that you can send the information in fewer bits. Okay? So rather than sending ASCII headers saying this is text or this is image, you can send binary headers. Okay? You can still do text, but you can do binary. The third thing you can do is you can compress. Okay? It uses on-the-fly compression so that the size of the request response is smaller. Okay? So rather than sending a long text document, why not compress it on the fly, send it because it's shorter, so you save network overhead, and decompress it at the other end. Okay? So it uses compression, but the most important part is it allows you to multiplex multiple concurrent connection over the same persistent TCP connection. Okay? And this is done through this notion called streams. Okay? So you have multiple streams of requests and responses that are interleaved on the same TCP connection. So you have each request and a response is a stream. Okay? So you can have multiple streams that are sharing the same TCP connection. There is no blocking because there's no sequential access. You can essentially do parallel. Okay? So that's your HTTP 2.0 that try to get over some of the overheads of 1.1. Okay? Now this is getting more common. Still HTTP 1.1 is the more common case, but HTTP 2.0 is being pushed heavily by companies that use lots of web services. So Google and others actually came up with this and have been pushing HTTP 2 a lot. Okay? And HTTP 3 or later versions actually do away with the need for having TCP as the underlying protocol. You can run HTTP over other types of protocol. There's one called QUIC, which is a UDP protocol. Okay, so you don't have the three-way handshake. You can do other things with it. So you can essentially run HTTP over other types of protocol. That's something that they're trying as well. So browsers like Chrome are actually at the front of supporting these types of technology. So if you use Chrome and you access any Google services, very likely it's using HTTP 2 or a later version. Okay? But if you are talking to other servers, maybe you are defaulting to 1.1 if it hasn't ever provided support for 2.2. Is that clear? Any questions here? All right. Your question, yes.
Does the quick use in the large network like web or other?
Okay, question is quick for a World Wide Web or it's a smaller area? We will get to quick in our later class when I get to maybe streaming. So let me give you a little bit of history since you asked that question. So quick was a protocol that was designed for streaming. Okay? So essentially YouTube and other services that were doing a lot of video streaming wanted more efficient ways of streaming. So and TCP has built-in retransmission, which sometimes is not useful. So they essentially came up with their own protocol that ran over UDP, which was called QUIC. Okay? Then so that was the origin of QUIC. Then they said, hey, this is a good protocol. Maybe we can run other things on it, and they're using it for other protocols as well, not just streaming. Okay? But it is designed to run over the internet. If that was your main question, it's not designed for something smaller like a data center and so on, because data centers can run their own variants or TCP that will not work on the internet. This is designed to run over the internet. But both the server and the client need to support it. Okay? By default, TCP and UDP are still the most common protocols, but there are new ones like QUIC that are emerging that lots of services support. Okay, but we'll get back to that in a later class. Okay, so I'm going to talk quickly about web services and then we will end it here. So web services are a way you can design your web application, okay, where the client and the server part of the applications are just two application components that are interacting with one another. Okay? In the typical web world, the client is a browser. Okay? There's a user that's using the browser, and the other end is a server that's a program. Okay? But think of a scenario where the client is one application, the server is another application, and they're just interacting with one another. Okay? Maybe using an RPC type interaction. Okay? So if you build applications that way, okay, and using web-like technique, you get web services. Okay? So web services essentially doesn't mean it's just a service. It means something specific, which is this is a web application that is built in a certain way where you have a client and a server that are talking to one another using web technology. Okay? And the way they interact is actually RPC-like communication. Okay? And we'll talk about that in just a moment, but you will see that here. There's a client, there's a stub, okay? And there's a communication subsystem, there's a server, that's a stub. That looks really like an RPC system. The only difference here is the protocol that they're using to talk to one another is called SOAP. That's a web services protocol. Okay? SOAP stands for Simple Object Access Protocol. Okay? And I'll show you an example on the next slide. So you're not using TCP to send data back and forth. You're using higher level techniques called SOAP. When we get to RESTful web services in 2 slides, you'll see this protocol is HTTP, not SOAP. Okay? So you're layering RPCs over HTTP. Okay? That is what RESTful web services do. But let's start with web services first. So here is an example of a SOAP request. Okay? You don't need to understand all of this. All it's showing you is it's an XML request. Okay? The entire request is essentially XML text that is sent. It has all kinds of headers and it has information. This entire request, the only thing you really need to know are these 2 lines where it is sending an alert. It's sending a message saying pick up somebody at 2 p.m. It's sending an alert to a user. So this request, this is like, think of it as an RPC request, is going to the web application. So this is the argument. That's the function you're calling, is the alert function. This is the string you're passing to it. So the other end will essentially send an alert to some other user and send that message to that user. That's what is actually going on here. But that's not really relevant from our higher level discussion. Higher level discussion is web services use XML. Okay? And you will see that there's a lot of baggage you have to deal with just to send one request with a string. Okay? There's all this extra information has to go. So that's another way to say web services are a heavyweight protocol. There's a lot of extra information that goes back and forth to make all of this work. Okay? Here's another example. So let me talk about RESTful web services, and then I'll show you another example. So because web services had a good idea, which was let's use web technologies to allow applications to interact with one another. Okay? But they were heavyweight, they never really took off. Okay? So many years later, some web designer said, why not change that SOAP protocol with HTTP? The basic idea is good. We want components to talk to one another. HTTP is a widely used protocol. So let's use HTTP for applications to communicate with one another. Okay? And then let's send RPC-like requests over HTTP. Okay? That gets you to RESTful web services. So it was a much lighter weight protocol for achieving essentially the same thing. Again, I already have explained this long time back. REST stands for representational state transfer. It's just a way to think about how do I exchange information between 2 application components using HTTP as my protocol, as opposed to standard RPC, which runs over TCP. Right? So you used Java RMI, you may have used socket communication, you may have used gRPC. They all run over TCP/IP. Okay? When you write RESTful web services, effectively you are implementing RPC-like functionality, but it runs over HTTP, so it's easier to understand and envision. Right? So you will use get request to make requests. Okay? If you want to make updates, send updates, you can use post and put requests. You can also support delete, but many of them don't. Okay? So you can use our standard HTTP request types to implement RPC communication. So that's really what web services do. And here is an example. Okay? So this example is a service is sending you stock information. So you are going to basically say get stock price, and here the company name is IBM. Okay? So that's your URL. So essentially the argument is embedded in the So this is the call you're making, that's the argument there, and then you're sending some extra header information. You send that off to this other application component. It processes that, sends back a reply, and here is your reply, right? So you will get an HTTP response. The response here is a small XML. It could be JSON, doesn't have to be XML, but so you're getting back IBM stock price as some value. Okay, so you are using HTTP to communicate back and forth. Now we have RPC running over HTTP, so everything is implemented as web services. This is how things work. And you did this in your lab, as you probably remember. That's what your lab asked you to do. You are using REST interfaces to talk between the application clients and the front end, or even the front end and the back end component. So those are essentially one way to think about it is you are making RPC calls between application components. They were all layered on top of HTTP. Okay? Here is the corresponding SOAP call. If you had implemented the same stock ticker application, you would send this long XML request, okay, and you would get another long XML reply, okay, and then that would run over SOAP. SOAP itself can be layered over many other protocols. So there's a lot of extra overhead. Performance tend to be much slower. HTTP is much easier, highly optimized for communication or the internet and so on. So it actually gets the job done much more efficient. Okay, so I'm going to show you one more slide and then we'll end here. This slide is comparing SOAP and HTTP. Okay, so this column is what SOAP does. That other column, second column, is what RESTful web services do. So you will see that SOAP is designed to be language agnostic, which means you can write SOAP application in many languages. It's platform agnostic, which means it will run on many operating systems. And it's transport agnostic, which means it doesn't even need to run on TCP/IP. It's designed to run on UDP and other protocols. Okay? Because RESTful web services run on HTTP, you cannot be transport agnostic. Your transport is set. It's HTTP. HTTP runs over TCP. You cannot change that, but your services can be written in any language, right? So it's language agnostic, and they can run on any OS. They can run on Windows, Linux. So you still get platform agnostic. Okay? So you're getting most of the benefits that gave up transport flexibility. Okay? This is designed to have arbitrary distributed applications where your n components that all interact in arbitrary ways. Okay? So you can write arbitrary distributed applications here. This is client server. Okay? Two components interacting with one another. You make a call, you get a response. So I think then of course that component can make other calls and so on. It's point to point. Okay? This uses all kinds of standards. There is a web service definition language. There's a web services compiler, just as you have RPC Gen and all these Java RMI compilers. So you have similar techniques here. Here there are no tools, right? You can write web application in whatever tools you want. There's no standard, but there are many tools. I shouldn't say there are no tools. There are no standard tools. You can use your own tools to write your web application. Okay? There is error handling here. It's extensible, heavyweight. Okay? This, so long as you know how to write web applications, is much simpler. Okay? Tied to the HTTP transport layer, much more efficient. Okay? So those are the pros and cons. Okay? It's really not very much use of SOAP anymore. It's good to know that they existed, but practically every web service that is using this type of concepts uses RESTful interfaces these days. Okay? Any questions here? We'll stop here. Next time we'll talk about web caching and think about how can we use caching and proxy servers in interesting ways.